So we will have Jose Lage present first, practical alternative for diffusing constructal network enhanced cold plates.
All right, good morning, everyone. I'm Jose Lage. I'm a professor of mechanical engineering at Southern Methodist University in Dallas, Texas. And the work I am presenting today had been done jointly by one of my graduate students, Derli Amaral Jr., who is now an assistant professor at Bridgewater College in Virginia. The title of my presentation is Practical Alternative for Diffusing Constructal Network Enhanced Cold Plates. Important words in here: practical alternative. That means if it is an alternative, it means that something else exists already, and what exists is not practical, and I'll explain why. And we came up with an idea to make what exists practical, so anyone can use in a little easier way. The other words that are important in here is diffusing constructal network, and I'll show you what is the genesis of this sentence and why constructal. And why is this important for heat transfer design? First thing I wanted to tell you a little bit about what constructal theory is. This is a relatively new theory. It's a physics theory that was born out of thermodynamics, and it has, I believe, a tremendous impact on the way that we design devices in engineering, particularly in thermal sciences. The main statement of constructive theory is written in here. It says that for a finite size system to persist in time, and that means to live, to exist, it must evolve in such a way that it provides easier access to the imposed currents that flow through it. This is a statement, and there are a couple of books already on this topic. Design in Nature is one of them. And this idea came from my PhD advisor, Professor Adrian Bejan, that works at Duke University, and is really making a tremendous impact in our areas of sciences, engineering, and even outside. These pictures that I showed in here, particularly the ones here on the bottom, is just a delta, river delta, the lungs, the air or gas region or ducts of the lungs, and a tree. And what these three pictures, which are natural structures found in nature, have in common is the following: three things. The first one is the conduits that transport whatever whatever is moving in these pictures. They go from a single and large duct, like you have in the river delta. You have large, the river area here is very large, and then it transforms itself in many and very small conduits. Same thing happens in the lungs. You have the trachea that is shown in here, actually a little bit higher. Then it bifurcates. It goes to different air ducts, and as you go deeper and deeper in your volume, these ducts become very, very tiny and in very large quantities. So there's a lot of bifurcation. So what you're having here in terms of transport is a transition from very strong flow, which is essentially a convective flow, to a very weak flow, which becomes essentially a diffusive flow. In the last picture, we have this essentially the same thing. We have a tree, we have a trunk in here, which is very large. It provides large area for a strong flow. And then you go through a bifurcation process that goes all the way to the tiny branches that we see at the edges. The idea between all these pictures, or the objective, let's say, all these pictures can be seen as a distribution of whatever flows from a point to a volume. So the objective here of a tree is to bring nutrients from a point, which would be the base of the tree, and cover as large a volume as possible, so the leaves that we have here attached to the branches can be exposed to solar radiation for the process to take place. If you keep this in mind, all these three commonalities in here, you can start conceiving, designing devices, particularly in heat transfer, in thermal engineering, that will follow this evolution. So we do have an evolution in terms of design, in terms of geometry, from simple to very complex. But now we are guided how we should go from simple to complex, and we can generate structures as complicated as this one in here. Now, just a note in passing here that in the past, like 30 years ago, no one will ever spend time or conceive this. People could notice and observe these structures and so on, but to have these structures and try to bring them into practice, to build structures 30, 40 years ago would be impossible. We didn't have materials that were capable for us to do that, and we didn't have manufacturing processes. So None of this, in terms of engineering application, would even be conceived if anyone were talking 40 years ago. The story is completely different today. Materials processing, material properties, and manufacturing processes have advanced a lot. And nowadays we can foresee building structures as complicated as the one showing in here. All this leads us to the main topic of this presentation, which started by trying to answer the question, what if I wanted to distribute a finite amount of high thermal conductivity material into a volume that is generating thermal energy? So here we have a sketch of a possible configuration. We have a volume here shown as a 2D plane. And this volume is made of a material that has a certain conductivity, KL, and it generates a certain amount of heat, here shown as a volumetric heat generation term. And this material has a certain volume, here shown by the height h0, the length L0, and the thickness W. Now, this study is going to be done primarily in 2D, so we consider this domain as being relatively thin, so W is small, and we don't concern ourselves much with the depth, all right? At least this in the beginning. Then later on, we will include and do analysis in 3D. Now, we know that if we don't have this high conductivity material that you can place right here in the bottom as shown, this material, as it develops, as it generates thermal energy in the volume, and you have only 1 point absorption of heat at a certain temperature T0, let's say, here is true where the heat generation will escape. After a certain time, when the system achieves a steady state, you find maximum temperatures right here on these opposite corners, on the opposite side of your heat sink, right? So now imagine, we start talking a little bit more about thermal processes here. So this could be a cold plate generating a certain amount of heat, and you have a material certain thermal conductivity. So the question of how are you going to distribute your high thermal conductivity material in this volume to optimize the reduction of this maximum temperature is related to the structures that we've seen before. In tackling this problem, you of course have an infinite number of alternatives on how to distribute this material in this volume to reduce your Tmax. But we started here with the simplest one. The simplest one is just to get a straight amount or a straight conduit of this material right at the center. And by doing that, because of symmetry, then you can achieve a strong reduction of maximum temperature in the corners. Now, for instance, when I first saw that, I said, well, why don't we do a diagonal placing of this material right from the heat sink point in here to the point of maximum temperature on both sides and distribute this material in two straight paths? Well, yeah, you can do that, but your system is just going to get initially more complicated. It doesn't change the end result, or the final structure will look pretty much the same. It will just be a little bit more complicated. In terms of your the region occupied by the high thermal conductivity material, we have in this particular case then length L0, which is the total length of the domain in this case, and a certain thickness D0. Now, with this system, with this configuration, you can define a delta T0 as being the difference between the maximum temperature in your domain and the temperature of your heat sink T0, and do a simplified back-of-envelope kind of analysis. You can apply a 1D heat transfer through the low conductivity material, which is shown by this area here. And this means that we are assuming that the heat transfer that flows from this volume to this heat sink in here, it's limited to the vertical direction in the low thermal conductivity material, and also a 1D analysis in the high thermal conductivity material, which is shown by this red arrow in here. If you do this simplification, it's possible for you to show, and I'm not going to do that in here, it's very, very simple. This is like an undergraduate level kind of problem, to show that your delta T0 can be written in this form in here. And this, of course, involves the volumetric heat generation rate that you have in your domain, the geometry of your domain, or the geometric parameters, H0, L0, and D0, and the two thermal conductivities, KL and KH. Interesting from this result is that if you non-dimensionalize your delta T0, then the equation takes this form shown in here, and here is very easy to identify under this form that the problem of reducing delta T0 becomes an optimization of the parameter H0 and L0 that, as we see in these two terms in here, has opposite effects. So you do have, or you fall into an optimization problem. You can optimize your system to minimize delta T0. So before I progress in here, these two simplifications imply two requirements that you have to have. One is that your H0 be much less than L0. This makes this distance in here much less than this distance, which supports the one-dimensional assumption for the low thermal conductivity material heat flow. And the other one is that your D0 be much less than H0, which then supports your assumption of unidirectional in the x direction heat flow in your high thermal conductivity material. This last one, by the way, translates into the volume of your original material, your V0, being much larger than the volume of the high thermal conductivity material. So the essential validity of the results shown in here have these requirements, geometric requirements, to back them up. So now that we have that expression for the optimization of L0 and H0, you optimize, you get the result, and this is the optimum ratio between the two. And this we can also see by looking at the results that these requirements and the previous ones, these requirements also have to apply. So the high thermal conductivity material has to be much higher than the base material thermal conductivity, and your H0 has to be much higher than L0. The result that we have in here now, as seen as 1, indicates that if, as a thermal design, if I have H0, D0, which are the height and size of my high thermal conductivity material here and the height of the original heat generating material set, and if I also pick the two materials, high thermal conductivity and low thermal conductivity, this equation in here essentially allows me to obtain what length L0 I should have for my domain to optimize the decrease in the maximum thermal conductivity that I obtain in my system. This geometry that I showed in here is identified by us as the first construct, and that is the construct with I equal to 0. This is the base construct from which I'm going to build my domain. How do we build it? Well, ideally here, what we do is, remember, we started with this domain here generating heat, and we ask ourselves, how do we distribute the high thermal conductivity material to optimize the cooling process? And then say, well, put here a strip of high thermal conductivity right in the center. Well, that then builds my first construct. And what I do now is, well, if I just place my first construct perpendicular to this strip now, what I do is essentially start building a very complex, geometrically complex structure. That's what we call a tree network, to cover the entire volume, and doing so achieve or aim at reducing your maximum temperature or facilitate the heat flow from the volume to the point. And that's what I mentioned beforehand. This structure that we are building here, that we are seeing evolve in time, essentially shows or looks like structures that we see in nature, the lung, the tree, the river delta. So we can place then these small constructs one next to the other. And now, after you place them in here, you see this structure as a homogeneous structure. You won't see, imagine that you reduce your visual resolution, you won't see this material in here anymore. So take yourself back, don't see this material in here, just see, as I said, as an heterogeneous region with an effective thermal conductivity. If you do that, you go back to your original problem, because now I have another material, another region in here that is generating heat, and I can distribute a high thermal conductivity material in the domain, and this region will have maximum temperature 0 in the corner. So essentially it's the same thing that I had before. So you go back to doing exactly the same thermal analysis, the same simplifications, assumptions, and you end up having exactly the same result. So you have now a process of building your structure from simple to more complex with this procedure of identifying your constructs and placing them in your domain with the objective to facilitate the heat flow. In this structure in here, which is our second construct, by geometry, you can see that now this height has to be twice this length in here. Remember, we assume that we have a very small volume of high thermal conductivity material, so this length here is negligible as compared to H1. This is one of our assumptions. And when we repeat the optimization, we then Now we have an expression for L1 optimum, which now is this length in here, the length of your second construct. And then, of course, you have to have some limitations in geometry by placing this initial constructs to fill up this volume. You want the number of constructs to be finite. You're not going to split a little construct. So you have then these requirements that are shown in here. And the ratio between H1 and L1, which is the ratio between this height and this length, in this particular case, to satisfy these geometric constrictions, to 2, right? So now that we have the process of building this structure, we go from the first construct to the second, to the third, to the fourth, and here I have shown the second, third, and fourth constructs. They don't go all the way to the edge of the domain because in this particular case, we have adiabatic boundary conditions all around the domain, all around the cold plate, except the heat sink point that we have on the left. So there's no need for you to waste your high thermal conductivity material going all the way to the right. So at the end, once you do all these processes of building your structure, you end up having something like this, which is our tree network. This would be an example of a complete assembly at level 4. So you can put
excuse
all
me,
this.
Jose.
Sorry?
I just wanted to let you know you have about, 3-ish minutes left.
Okay, all right.
Sorry.
So these then are the results of your optimization. This is the guiding, a table for us to build the structures. And all this was done considering placing your high thermal conductivity embedded in your heat generating volume. Well, that's the part that we are concerned with, because if you have a heat generating volume, let's say an electronic board, it's not practical to assume that I can distribute a high thermal conductivity material embedded in it. So I say, well, that might be relatively easy. Just put your network on top of your heat generating volume. So that's the part that concerns the making it practical. So we selected a couple of materials for our analysis in comparing the two, the embedded, which we call in plane, and the top, which we call out of. Some geometric parameters were chosen. This is very ad hoc, but we wanted to make it practical, see how this thing will work. So we chose copper for the high thermal conductivity material and assume a resin for the low thermal conductivity material. Did calculations and verify if our domain were satisfying the requirements of our analysis. And to do that is extremely difficult. Of course, we have to go to our smallest possible entity or construct in the domain, and you have to fix how small that can be manufactured. And we use 2 millimeters for the thickness in here. We believe that smaller than that, it becomes very difficult to deal with, to build it. And then we start looking at, what happens if we have 1 construct, 2 constructs, 4 constructs, what happens with the complexity, increasing complexity. It's extremely difficult to even design these structures because you have a lot of constraints. You have the volume of material that you start with, you have the volume of the material that you have available, and you have tolerances for manufacturing, so on and so forth. So we combine a CAD 3D with an Excel sheet for parametrically linking the two and iterate. You have to start from the smallest structure to the largest to be able to get results. So once we have the structures, then we went on and did numerical simulations. This shows the balance equations and the boundary conditions. This also is not trivial because you're dealing with an heterogeneous system with very, very irregular geometry, as you can see in here. These are the 6 geometries that we study, and some of them are square, like 2, 4, and 6, and some of them are rectangular, 1, 3, and 5. And these are, as I mentioned, consequences of trying to fit all the geometric requirements. Then we went on and did numerical simulations, and we have 2 objectives in here. First, to show how efficient this network is, and second, to show how different it is if I put the network embedded in the heat generating volume or if I just place it atop the heat generating volume. Here are qualitative results shown with this temperature distribution on top is for the in-plane network embedded, and the bottom is the out-of-plane. At least visually in here, it doesn't seem like there is any difference between the two, which is good. Then we also compare the numerical quantitative values of maximum temperature. This is non-dimensional, of course, for a certain ratio of thermal conductivity. And we observe that the cases for aspect ratio equal to 1, the square cases, show a small decrease as we increase the complexity. as we would expect for both cases, the square and the rectangular. And here we show then the effect of changing your thermal conductivity ratio. And these results are actually very interesting because it shows that when your thermal conductivity ratio is small, like 10, 30, and even 100, the effect of increasing the structure of your tree network is not very big. It does impart in a reduction in your maximum temperature, but that reduction is not too big, right? Now, when you go to a higher thermal conductivity ratio, 800, 3000, 8000, the effect is tremendous. So you really can have a tremendous effect in reducing the maximum temperature of your domain if you know how to distribute it and if you do this tree network structure for your system. Here is just a summary of the evolution. This is for the out-of-plane case, which is the practical case shown if you go from thermal conductivity ratio of 10, in which the high thermal conductivity and low thermal conductivity are not too dissimilar, all the way to 8,000. And what you see is just an enhancement of your visual resolution, because when this ratio is very, very high, the result of that is making the temperature distribution in your high thermal conductivity material becomes almost isothermal, because the thermal conductivity is so high that you won't need a large temperature gradient. That's why it becomes more visible in the picture. All right, in terms of summary and conclusions, we tested 6 distinct optimal T-shaped networks for increasing complexity. It is very difficult to practically satisfy the constraints, the geometric constraints that we have in this problem of the original design. The design has been shown to be very robust. Our structures, they do not satisfy all the requirements that we have. Our high thermal conductivity volume, for instance, is not much smaller than the original volume. It's in fact almost comparable. It's a factor of 2, 3, 10, but it's not much, much smaller. Nevertheless, the structures, they perform extremely well. We also observed that there is an increased cooling efficiency as the thermal conductivity ratio goes beyond 100, and for 800 or higher, this effect tends to disappear after your structure reaches a complexity level of 3. So it doesn't pay off for you to go to much higher complexity, because you won't gain much in terms of reducing the maximum temperature of your system. And the final conclusion, which is very important for us, is that if you just put your network on top of your heat generating volume, the system works as well as if you put it embedded. And that shows that the out-of-plane option, design option, is as efficient as the in-plane option. All right, that's what I have. So if there are any questions or comments, I will certainly entertain. And thank you very much for attending. And thank you, the presenters, for accommodating my request to change my time, because I have to teach a class today at 10.
No, definitely not a problem. Thank you for presenting your work. This is very interesting, and I love that it's kind of, following what nature has designed on its own. So I think at this time we don't really have time to ask you questions over the phone, but if you do have time, if anyone has any questions in the chat and you can answer in the chat, we can do it that way so that we can keep moving along.
Certainly, absolutely.
Okay, thank you.
Thank you.